Welcome to the deep dive. Today, our mission is to unpack something that sounds incredibly small at first. We are looking at how a microscopic change in just literally a single line of code can fundamentally alter how an entire system flows.
Right.
And it's a really specific optimization we are talking about today, but it opens up this much larger conversation about how we design digital architecture for a world that is, just inherently unpredictable.
It really does. It serves as this perfect lens for understanding how digital infrastructure is actually maintained under the hood.
Yeah.
When we so often evaluate technology in terms of just raw throughput or processing power.
Oh, absolutely. The speed of it.
Exactly.
Yeah.
But today's source material forces us to reevaluate that metric completely. It highlights why systemic flexibility and the ability to gracefully handle partial data is often far more critical than demanding perfect synchronous execution.
Okay, so let's unpack this. Our source today is a concise, highly focused blog post. It was published today, actually, March 10th, 2026.
Hot off the presses.
Right. It's written by a developer named Qianmeng Eng, and the post is titled Notes on Haskell Programming, Part 78, A Quicker Way to Read a File.
Part 78. That detail matters.
It really does. We are looking at a specific API swap in the Haskell programming language. But before we get into the heavy stuff, the buffer management and I/O execution, the context of the person writing this code is critical. You really have to understand his philosophy to understand the optimization.
Yeah, because his background completely informs his approach to the code base.
Yeah.
If you look at his bio, he doesn't refer to himself as some disruptive tech visionary or anything like that.
No, not at all.
He simply calls himself an old software plumber. And he says he spends his nights tinkering with free library and open source software.
But I love that terminology, software plumber.
It's incredibly grounded, right?
Yeah.
Because think about what plumbers actually do. They maintain the hidden, unglamorous pipes that we all rely on every single day without ever thinking about them.
Until they break.
Exactly, until they break. And software developers who maintain Floss projects, free libre and open source software, they do the exact same thing for our digital world's infrastructure.
You definitely see that commitment to the foundational layer of the internet in the organizations he actively supports on his site. He lists the Electronic Frontier Foundation, the Free Software Foundation.
The Tor Project, Wikipedia.
Yeah, the Software Freedom Conservancy. He is deeply invested in the open, accessible layers of the web. But for me, what truly stands out is his commitment to operating in public.
Oh, the sheer scale of his output.
It is staggering. He treats his blog as this open ledger of his learning process. I was looking at the archives, and in 2025 alone, he published 730 posts.
Which is exactly 2 posts a day, every single day.
Every day. And he's maintained that rhythm for years, going all the way back to 2011.
That level of disciplined output reveals just a relentless curiosity. And the fascinating thing is, it's not restricted to software plumbing.
Not even close.
If you look at the archives surrounding this specific Haskell post from March 2026, he is simultaneously publishing notes on gardening part 829.
Part 829, what is he even writing about in that one?
He's analyzing a nostalgic mustard plant, and he's getting into the structural issues of leggy seedlings.
Leggy seedlings.
Yeah. And right next to that, you find notes on fish keeping part 207, where he is breaking down the mechanics of simulating a monsoon season in an aquarium.
Wait, simulating a monsoon? Why?
To trigger behavioral changes in the fish. It's fascinating.
Okay, so you might be listening to this and wondering, why should I care about his fish or his mustard plants when we're supposed to be talking about a Haskell console program?
It's a fair question.
But it's because elite technical problem solvers almost always exhibit this polymath pattern. To be truly well-informed in tech, it really helps to study everything else. They draw architectural inspiration from observing complex natural systems.
Right. Because when you spend time observing how a biological ecosystem thrives or fails, like how a plant reacts to suboptimal light or how an aquarium responds to shifting environmental constraints, you are actually studying systems design.
You are learning about inputs and outputs.
And above all, adaptability.
Yeah.
A software application is really just another ecosystem. And that biological adaptability, the ability to process whatever the environment gives you rather than waiting for ideal conditions, is the exact concept at the center of the code optimization we're looking at today.
So let's dive into that technical problem. He is trying to optimize how a Haskell console program reads an input file. And he identifies a major bottleneck in how the application handles data ingestion.
Yeah, the ingestion phase is where everything was getting jammed up.
Right, so the program needs to take in data. And the original function he was using to execute this read operation is called hGet. Now, hGet has a very strict operational profile.
Very strict. It's rigid.
Yeah. Think of it like this. Imagine you are sending a friend to the grocery store to buy exactly 1,024 apples.
That is a lot of apples.
It's a huge party. But seriously, imagine you send them for exactly 1,024 apples. If the store only has 512 apples in stock, your friend refuses to come home.
They just stay at the store.
They literally just stand there, blocking the aisle, waiting forever for the rest of the apples to magically appear so they can fulfill the exact order. They won't bring you the 512 they already have.
That is exactly how hGet operates. When you invoke hGet in your code and pass it a specific buffer size, say 124 bytes, you are issuing a rigid command. hGet will demand exactly 24 bytes before it returns control back to the application thread.
And what happens if it doesn't get all 124 bytes right away?
The file handler will literally block. It insists on reading the exact amount, it puts the thread to sleep, pauses execution entirely, and waits until every single byte is collected or until it hits the absolute end of the file.
Which feels like a massive liability.
Right.
Especially in any kind of unpredictable environment. We all know the pain of a blocking I/O call hanging up a whole application.
It's essentially mimicking the behavior of the old C standard library's thread function. You ask for a block of items, and it stubbornly waits to fill that block.
Now, in a purely local context, like if you are reading from a super fast solid-state drive on your own laptop, maybe you don't notice that blocking behavior.
Right, because the disk is so fast, it populates the buffer almost instantly.
But the moment you introduce any kind of latency into the data stream, a blocking read like hGet becomes a system-wide bottleneck.
And the overhead of that blocking is severe from an architecture perspective. Think about what happens under the hood. When a thread blocks waiting for I/O, the operating system has to perform a context switch.
It has to physically move resources around.
Exactly. It suspends the thread, saves its state, and schedules another thread to run on the CPU. Then, when the remaining data finally arrives, the OS has to fire an interrupt, wake the thread back up, and perform another context switch just to resume execution.
Which sounds exhausting for the CPU.
In a high concurrency application, it absolutely is. If you have hundreds of threads constantly blocking and waking up just to fill arbitrary buffer quotas, you are burning incredible amounts of CPU time just managing thread states. You aren't actually processing data.
And in a language like Haskell, which leans heavily on pure functions and often utilizes lazy evaluation, forcing strict I/O blocking just feels counter to the broader philosophy of the language.
It does. You want data to flow smoothly through your pure transformations. You don't want it getting bottlenecked at the boundary layer just because an I/O function refuses to hand over a partially filled buffer.
That is the architectural trap, isn't it? Designing for the ideal scenario rather than the messy reality.
Yes. hGet assumes the data source is perfect, immediate, and neatly packaged. But if you're building a resilient system, you simply cannot design around perfect inputs.
You have to assume reality is going to intervene.
You have to assume the data will stutter, it will delay, and it will arrive in fragmented chunks.
Which brings us to the tiny API change that fixes this whole problem. Qian Meng introduces a tiny shift to solve this fragility. He swaps out hGet for a function called hGetSome.
Just adding the word sum changes everything.
It really does. As the name implies, it's a shift from demanding an absolute rigid quantity to accepting whatever is currently available.
It's a much closer wrapper around the raw Unix read system call.
So how does it differ in practice?
When you invoke hGetSome with a 1024 byte limit, you are no longer saying, block my entire program until I have 1024 bytes.
Right?
You're saying, give me whatever is currently waiting in the file descriptors buffer up to a maximum of 124 bytes and return immediately.
So it reads up to 124 bytes, but crucially, if there are only 512 bytes sitting in the buffer, it doesn't sit around waiting like our friend in the Apple aisle.
No, it grabs those 512 bytes, flushes them directly to the application, and hands control back to the execution thread without a microsecond of hesitation. It completely bypasses that artificial waiting period.
The program just takes what it can get and keeps moving. It prevents the entire system from freezing up over missing data.
Exactly. By returning partial buffers, hGetSome allows the main application loop to keep moving. The process can immediately start parsing or transforming those 512 bytes, while the OS quietly accumulates the next chunk of data in the background.
You transform a stop-and-go bottleneck into a continuous pipeline.
You are prioritizing the continuous flow of the application over the neatness of uniform data chunks.
The program adapts to the environment rather than forcing the environment to adapt to the program. But here is where Qian Meng points out a really surprising fact in his text. It's a bit of a speed paradox.
Right. He admits something pretty interesting.
He notes that despite the title of the article being a quicker way to read file, for their specific current use cases, you might not even notice a huge shift in raw speed.
Which is counterintuitive for a developer blog post.
Totally. Usually when developers dive into the weeds of I/O functions and buffer management, they are hunting for those massive millisecond performance gains. They want to show a benchmark graph where the new function is twice as fast.
But he pivots completely away from raw execution speed. So you have to ask yourself, why even bother making the change?
He says the core reason is that using hGetSome is simply technically safer.
Technical safety. That's a fascinating term to use here, because normally when we talk about safety in systems programming, we usually mean memory safety, like preventing buffer overflows or dangling pointers.
But he's talking about architectural safety. He details exactly where this safety is needed the most, when the console program is receiving its input via Unix pipes.
Pipes are essentially how different programs pass data to each other.
Right. The Unix pipeline is the foundational architecture of command line tools. You take a series of small utilities and chain them together. The standard output of one program becomes the standard input of the next.
You're creating a continuous assembly line of data processing.
But a pipe is not a static file sitting on a hard drive.
No, it is a live, dynamic channel between two completely independent processes. And the process feeding data into that pipe might be slow.
It might be doing heavy math or waiting on its own database query before it spits out its next line of output.
Right. So if your Haskell program is sitting downstream in that pipeline and you are using the rigid hGet function, you are completely at the mercy of that upstream program's cadence. Your process will stall, constantly waiting for the chunks to fill up.
And he pushes the analysis even further. He makes this big connection for the listener that I think is the key to the whole post.
The network connection.
Yes.
Yeah.
He points out that reading from a pipe behaves a lot like reading from a network stream. Data over a network doesn't always arrive perfectly packaged.
It never arrives perfectly packaged. Network data is inherently chaotic. You have packet fragmentation. You have TCP windowing adjusting the flow rate on the fly. You have network congestion causing packets to drop.
A 1024-byte payload might get split across multiple TCP packets. The first packet arrives instantly, but the second packet might hit a congested router somewhere in Virginia and get delayed by 100 milliseconds.
And in CPU time, 100 milliseconds is an absolute eternity.
It's lifetimes.
If your application relies on hGet to read that network stream, a slight network hiccup crashes your process, or at least paralyzes it. Your thread sits there, holding onto the first half of the payload, doing absolutely nothing, just waiting for the rest of the bytes to arrive.
And if you extrapolate that across a system handling thousands of concurrent network connections, that strict blocking behavior will catastrophically degrade your architecture.
You end up with thread starvation. Your server stops accepting new connections, not because the CPU is maxed out, but because all your worker threads are parked in a suspended state, waiting for rigid buffer quotas to be met by a stuttering network.
So hGetSome accepts the unpredictable flow of reality.
Exactly. The safety he is talking about is system resilience. By swapping to hGetSome, you decouple your application's execution state from the unpredictable latency of the outside world. When the first packet arrives, hGetSome pulls those bytes and returns immediately. Your application handles the stutter gracefully.
It's the difference between a brittle system and a resilient one. A brittle system demands the external world conform to its internal expectations. It says, I process data in 1024-byte chunks, and if you can't provide that, I'm shutting down.
While a resilient system one, built with functions like hGetSome, acknowledges the chaotic reality of data transit. It accepts partial payloads, absorbs the jitter, and keeps moving forward.
Which brings us full circle back to his fish and his mustard plant.
It really does. This is exactly why observing natural ecosystems translates so well into software engineering. In nature, biological processes don't block and wait for ideal conditions.
Right. A seedling doesn't stop growing entirely just because it didn't get its exact quota of sunlight today.
It stretches, it becomes leggy, just like he wrote in his gardening post. It adapts to process whatever light is available. It utilizes an hGetSome approach to survival.
It takes the partial input and iterates.
Yes, and that biological analogy applies directly to the author's own methodology. The deeper you look at this tiny code-based optimization, the more you realize it's a reflection of his broader philosophy on life.
We're looking at a single post out of 730 published in a single year. Qian Meng isn't demanding a fully complete, perfectly polished 10,024-byte block of knowledge before he hits publish.
He treats his life as a series of small, continuous iterations rather than demanding a perfect, finished product right away. Think about the titles of his archives. Notes on Haskell Programming, Part 78.
He didn't lock himself away for a decade to write the definitive textbook on Haskell, refusing to release anything until it was absolutely perfect.
He processed a small insight, a realization about buffer management, and he immediately flushed it to the public. He takes a partial chunk of data, processes it, publishes it, and moves to the next loop.
By refusing to block his own publishing pipeline, waiting for a massive masterpiece, he ends up generating a far more robust body of work over time. He didn't become an expert overnight. He wrote 78 parts on Haskell, 207 parts on fish keeping, and 829 parts on gardening.
It prevents intellectual deadlocking. How often do we stall our own projects, whether it's learning a new technical skill, or writing a piece of code, or starting a business, because we are operating like hGet?
We demand that all our resources, all our knowledge, and all our time be perfectly aligned and fully buffered before we take a single step forward.
We block our own execution waiting for perfect conditions.
So to summarize this deep dive for you listening, a tiny shift from hGet to hGetSome teaches us that in systems, whether we are talking about software or life flexibility and adaptability, often trump rigid expectations.
And it leaves you with a final thought to mull over today. Think about your own projects. How much more resilient could your own learning process be if you stopped waiting for the perfect 1024-byte chunk of inspiration and instead just started processing whatever small insights are available to you right now?
Stop blocking the thread and start processing the stream.
I love that.
That is all we have for today. Thank you for joining us on this deep dive. Take that final thought with you, explore it on your own, and we will be back next time to unpack another fascinating set of sources.